Good afternoon, ladies and gentlemen. My name is Gavin Perry, and this presentation is for Workforce 105 for Pennsylvania State University. The course we're doing today is seamanship, and we're covering tides and weather patterns. I know they're two separate topics altogether, but they're so intrinsically tied together that we don't want to pull them apart even if we could. So the course objective for today is to gain a better understanding of the major causes for wind and tide, and to understand the behaviors within the hydrosphere and atmosphere, and that they are just two of the four major spheres found on Earth that also include the lithosphere and biosphere. I'm going to bring them up, but we're not going to cover those today. In actuality, there's 17 spheres, cryosphere being one of them, and just to give an example, that just means the frozen part of the Earth. So we're just going to talk about the four major spheres. And we're also trying to spark an interest in the environment around us. You being a part of the environment, hopefully, if you haven't already been exposed to any of this information, you do gain an interest in this because, well, again, you're part of that environment. So the terminology we need to know is atmosphere, the envelope of gases that surround the planet. The hydrosphere, the total amount of water found on the surface of the planet, including underground or in the air. It can be liquid, vapor, or frozen. Also, you don't have to know, but just know it exists. The lithosphere, it's a rigid part of the Earth consisting of the crust and upper mantle. And finally, the biosphere, the regions of the planet occupied by living organisms or the zone of life. And as we know, people are finding new life all over this planet the more we explore it. So who here believes that the Earth is perfectly round? Well, it isn't. And no, it's not flat either. The Earth is better known as an oblate spheroid. An oblate spheroid, simply put, means a sphere that is flattened out at the top and bottom, causing the center to be a little wider. A little like a water balloon after being filled up in the sink and placed on the counter right beside it. You as children have all done it. I know I've done it myself numerous times. But the reason why that balloon flattened out is because of gravity. The reason why the Earth is flattening out is because of centrifugal force or centrifugal force. So here we have an example of the oblate spheroid. So like the water balloon, it's flattened out, but not completely flat, just a little bit. We'll get into exactly how much soon. And then over here is called the prolate spheroid. Just so you know it exists, but not what we're going to cover here today. So the squat Earth is about 42 kilometers wider than at the equator than it is from top to bottom, pole to pole. This means that an object is 21 kilometers further away from the center of the Earth at the equator than it would be at the poles. That's about 0.3% of a difference overall, but still enough to have a large enough impact on the natural environment we live in, especially on the atmosphere and the wind patterns. The spinning action creates friction within the atmosphere, which is a large cause of the wind patterns we experience. The remainder of the cause for wind is the uneven heating of the surface by the sun. The Earth spins much faster at the equator than it does at the poles. This was studied by a French mathematician named Gaspard Gustave Coriolis and published a paper called The Collision of Spheres in 1835. His area of study and interest was friction, hydraulics, and kinetic energy. And here we go, the Coriolis effect. Now, if you follow the laser pointer, I'm pointing at the equator. That's where it's spinning the fastest. So all the wind is being pushed down and out towards the lower spinning poles. So in a low pressure system, if we include induction or convection, later on we'll cover that, but the low pressure system, they rotate counterclockwise, and south of the equator here, is the exact opposite. It's the low pressure system is going to rotate clockwise, as described here on this diagram. So we have the high pressure system rotates clockwise, and the low pressure system rotates counterclockwise. This is only in the northern hemisphere. That's going to be the exact opposite in the southern hemisphere. When we factor in air temperatures and the fact that cooler, denser air originating from the polar regions likes to travel towards the equator, where the warmer air has less density, as the cooler air makes its journey towards the equator, it warms and begins to gain altitude. We then can accept the fact that the warm air traveling away from the equator likes to remain aloft for a short time until it cools and begins to descend. This is called convection. When we have coupled together our understanding that air temperature has a vertical direction of travel and the fact that the Earth is spinning, they combine to create our cells. That brings us to our video. We have the end of this chapter is a nice little short video. Hopefully the volume's up high enough for you guys at the back.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise, and that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video, and that's kind of the point. I hope you got what you came for. And the Coriolis effect doesn't really influence toilets, they're just really too small, and the direction of the spin more depends on the placement of jets inside the toilet. But that's it, that's the Coriolis effect. If you like this short and to the point video...
Well, they answered an age-old question. Which direction does the water flow south of the equator in the toilet? Well, it doesn't really matter, does it? Okay, so thank you, Gustav Coriolis, for that. On to our next section here. Wind. If the wind is moving in a clockwise direction and we're in the northern hemisphere, then chances are that nice days could be on the way as pressure could be building. Conversely, if the wind is moving in a counterclockwise direction, then we could be in a low pressure system which is less stable and an invitation for storm. Of course, temperature and the seasons play a large role in determining weather patterns as well. I encourage you on your own time and at your own leisure to study the subject, as it's quite involved. The study of meteorology, also a prerequisite for a pilot's license, can cover this in more depth. So on one of your blank sheets of paper, I'd like you guys to write out a short little statement on what is convection and how does it play a role in our atmosphere. You can turn that in at the end of the day today. So it brings us to part 2, the ocean, and the effect of gravity on the ocean. There you go. Clickers. That's a nice picture. Kind of like that one. I'm going to hold there for a sec. Okay, so now the terminology. You guys can take notes if you want. Neap tide. When the moon is at 90 degrees to the sun from the earth, the bulge is diminished. The bulge you're talking about is the ocean's bulge. We'll get into that a little bit deeper here in a second. Because the sun is now pulling on the lower water in the middle of the two bulges, our high tide is not as high as it would otherwise be. Neap is an Anglo-Saxon word meaning without power. And that brings us to spring tide, the polar opposite of neap. The term spring has nothing to do with the time of year, but everything to do with the idea of leaping or jumping. Also called the king tide. It's used for this event. The spring tide happens when the moon is directly between the sun and the earth and the gravitational forces combine, resulting in a stronger pull on our ocean. Just magnified the effect. And here we have ebb. As the continents pull away from the ocean bulge, held in suspension by the moon's gravity, the water level drops, exposing more of the landmass. Depending on topography of the landmass, we could see more or less exposure and experience greater currents if a certain volume had to travel through a restricted space. And flooding. Now this is where the danger kind of rolls in. When the water is rising, in this case due to the earth rotating into the bulge of the ocean, water held by the moon, it's called the flooding tide. I guess they're going to cover here the dangers of flooding here in a second. We all know that the ocean responds to the pull from the moon and to a lesser degree the sun, but what is far more interesting is that the moon isn't really pulling the ocean around our planet. Because the moon takes 28 days to make one rotation around the earth is actually spinning through the ocean. I know, I was shocked just as much as you are now when I first heard that. Because the moon takes 28 days to make one rotation around the earth is actually spinning through the ocean. Our planet takes 24 hours to make one full revolution in space, as evidenced by the sun and our night-day cycle. This is called a solar day. You guys are going to learn about both types of days. We have a lunar day and a solar day. The tide is one of the most reliable phenomena and a form of measure, but there's a delay of 50 minutes from one day to the next. Because the moon spins around the earth in the same direction the earth is rotating, the earth has to do a little catch-up of about 50 minutes for the same point on earth to reach the moon's new position in the sky. That's called the lunar day. Of course, there are exceptions to the rule, and the exception in this case is topography. In a few places, there is one tide a day. Here's this nice diagram I like. Here's our bulge that we were talking about earlier. Always pointing towards the moon, the highest part of the bulge. And wherever the moon is, not 90 degrees to the moon, is always going to have a low tide. And opposing the highest tide here, the high water bulge, we have another bulge. That's from the gravitational pull of the moon itself acting on the planet, not just the water. On the previous slide, we can see the bulge of the ocean as it rises up towards the moon. This is a permanent bulge. The highest point being the closest to the moon, with a corresponding smaller bulge on the opposing side of the earth. As a consequence of these two bulges is that the water between them is quite low, giving us our low tide as the earth rotates. On the next slide, we'll look at neap and spring tides. The moon, due to its proximity to Earth, is responsible for twice the gravitational effect than that of the sun. When the moon is between the sun and the Earth, we get a combined gravitational pull on the ocean, giving us our highest tides. And here's our next slide. There we go, there's the moon. It takes 28 days to make one rotation around the Earth. But the Earth is spinning, it takes 24 hours to make one full rotation. And look at that, the sun even has its own rotation of 27 days. So you can see the ocean is always sitting right there. The bulge of the ocean is always pointing right at the moon, like an angle indicator. So the Earth is spinning right through that bulge. Pretty amazing stuff. For this example, we'll focus on North America. The flooding tide as we see it travels from east to west, so that the water must travel northward on the west coast, then eastward across the Arctic, and finally southerly on the east coast. The entire system of navigation and navigational buoys is built around this principle and called buoyage. Here we go, North America. And just assume that the bulge is coming up against the west coast. It's got nowhere to go. It can't go over the land. It's got to go north. And then around Alaska. And then eastward. And then southerly on the east coast. That is a flooding tide. Now the further you study into buoyage, you guys will learn about this in a much deeper, in much greater depth. But it's interesting to note that the water, the high water has to come up, the high tide has to come back around Alaska. We get some very, very high tides there, like 24-foot tides in some places. In Prince Rupert here, we have 12-foot tides. But here in Alaska, they got 24-foot tides. Amazing. I know a guy that lost a car because he parked at low tide on a boat ramp. Okay, here we go. Here's the moon. That's 90 degrees to the sun. There we go. I like that zoomed in a bit better. So here's the moon. It's 90 degrees to the sun. So it's pulling that bulge. But of course, we're going to have here a neap tide, not a spring tide, because the sun is going to be pulling on the low water part here. So this is a video. We're going to play this short video and then we'll continue on from there.
Tides are caused by the moon's gravitational force pulling on the Earth and its oceans with different strengths. The pull on the near side ocean is the strongest because it's the closest, so it moves most towards the moon. The Earth also moves towards the moon, but not so much as it's further away. Finally, the far side ocean moves towards the moon least because it's farthest from the moon. These movements due to gravity create 2 high tides and 2 low tides as the Earth rotates through 24 hours. But there's a big object that's missing from our diagram. If we back up, we can also see the sun and how it lights up both the Earth and the moon into their day and night sides. We'll turn off the stars to make it clearer. When the moon is right in front of the sun, it's invisible to us because we can only see its dark night side. This is the new moon position. You can see that each day corresponds to 1 Earth rotation. In just over 7 days, that is 7 Earth rotations. The moon orbits around the Earth to its first quarter position, where we can see half its day and half its night side. After another 7 days or so, the moon orbits to the opposite side of the Earth, to the sun, and we can see its full day side. This is the full moon. Then it continues onto the third quarter, before returning to the new moon position to start all over again. Does the sun also pull on the oceans and make them bulge like the moon does? Yes, everything causes gravity, and the more massive the object, the stronger it is. But this diagram isn't to scale, and the sun's much further away than the moon, reducing its tidal effect to about half that of the moon's. But this is important when the sun and moon line up so their gravitational attractions combine to make supertides. This happens at the new moon, making the high tides higher and the low tides lower. This extreme tide is called a spring tide. But when the moon goes into the first quarter, the gravities pull in different directions, and the sun actually takes away from the moon's tidal effect. The high tides are not so high and the low tides are not so low. This more moderate tide is called a neap tide. At the full moon, the moon and sun's gravities line up again, so we get another spring tide. At the third quarter, the gravities are out of whack again, so we get another neap tide. Then back at the new moon position, the moon's gravity combines with the sun's to start over again with another spring tide. Each month, the Earth spins almost 30 times, so we get nearly 60 high tides and 60 low tides. Of these, 2 are spring tides and 2 are neap tides.
Well, as you can imagine, people that lived a long time ago that didn't have watches and calendars, they would follow this very closely so they would know what month it is. Okay, so continuing on, we're going to talk about the continents affecting tidal lag. The depth and shape of the ocean coupled with the distance between the continents can play a factor on timing of the tide. The delay caused by these things is time between the passage of the moon and the tide's crest, giving us the term lag. Topography causes variation. In the middle of the ocean, the bulge could be just about 3 feet high, depending on the land shape. The variation between high tide and low tide could be 50 feet. Storm tides and surges, episodes of unpredicted high water on the tide table or a loss of low tide can be attributed to strong wind and increased by a low pressure center. If a combination of high tide, strong wind, and a low pressure center were all to happen at the same time in the same place, we could see flooding and the need for evacuation. So we have another question here. This one's a bit of a trick question. But on your piece of paper in front of you, you're going to have to give me a statement here on what does the ocean bulge, at what speed does the ocean bulge travel around the globe, and is it really racing around the Earth? Short statement, doesn't have to be too long. It's a bit of a trick question, but have fun with that one. Hand it in at the end of the day. That's the end of the class. As you can see, it's a very deep topic, and you could spend a lifetime learning it, really. Have a great day. Thank you.